castle where the digital dreams come alive. CESCG takes place from May 1 to 5, from visualization to the virtual space. Scientific sessions take their place.
Let's begin by getting a little bit into the background of this. The origin story of this talk dates back actually all the way to the last year when I was writing my project of dissertation. And at the time I was working for an unnamed German startup specializing in 3D printing. And we had this particularly large data set of very large meshes. And they were each called something like bottom left stomper. Now, I can probably see like you have no idea what a bottom left stomper is. I can assure you this is not a dance move. So I tried to view them in MeshLab and in Blender, and it didn't really work out very well, because all the app does is you fill up the process memory and the app freezes and you're pretty much done. So I figured, let's do something about it. The practical applications of this data is generally in the area of 3D scanning, where you have very large meshes. This one is a very recent example on the internal study of the bust of Apollo. This is the file size, and as you can see, it has 55 million vertices. So it's pretty large. I tried it in Blender, I tried it in MeshLab, doesn't work. So there are three main challenges to this problem. The first one is the conversion of the raw data to the app's mesh representation. Then you need to somehow figure out how not to fill the app's memory entirely, and then there's the rendering part where you already have some sort of reliable representation, and then you want to render it to the scene. Common decimation techniques, you probably know some of them, solve these issues, but actually introduce a severe preprocessing bottleneck. So you have to wait. You just have to run the algorithm on this data for a while. You go shopping or something, and then you're done. So if you don't want to wait that long, I have a proposal. Why should we use all of the raw data when only a reasonable subset will suffice? So some of these methods were already attempted by some streaming algorithms, by Eisenberg for out-of-core compression. Then there's some work done for the previewing of meshes on phones. And there's this very interesting example in JavaScript, actually, in 3JS, called the pop buffer. So it divides the space into a bounding volume hierarchy and then progressively loads the data. And then we, of course, must not forget the state-of-the-art Nanite, which generates these clusters and views them according to a direct-to-the-cyclic graph cut, so that was also mentioned here. But the problem with all of these approaches is that all of them require pre-processing. So how do we not do that? How do we simplify all of the mesh data without pre-processing? So this is the Apollo dataset. It's a binary PLI file from the 3D scans. The vertex data is ordered in some size with some stride, and then you have some vertex index data for the polygons. This is the original question. And first assumption that we're going to make is that this vertex data, the actual spatial data, is in a contiguous memory block with some stride, so we are able to read regular blocks of it and figure out where the actual coordinates lie. So that's the first assumption. And this of course, yields the opportunity for multi-threading. So we can divide this whole block into some number of worker threads and sample them. And then the second assumption that we're going to make is that the combinatorial data for the polygons is at this point irrelevant. So we're not going to use them. The sort of working version of this, which has already been tested, looks as follows. So this diagram basically says that a user puts in a file, then there's this sort of builder object that creates this strategy which samples the raw data on the file. And then there's this dispatcher object which controls the progress and the update functionalities. And then there also has to be an update queue, so all the work from the different threads can combine into different updates in a queue-like fashion. So this is the sort of pseudocode for the loop inside the vertex sampling part. Then the result will have to be meshed. So we only have like a point cloud from the sampled points, and we want to triangulate it, so we have a couple of options. The sort of industry standard is the Poisson reconstruction, which is also used by this very similar article using the PCSnet for simplifying point clouds. But the problem is that the Poisson reconstruction requires normals. So we don't have normals for in all data sets. Then there's the ball pivoting algorithm. And the particular thing that about the ball pivoting algorithm is that we need to state the ball radius explicitly at the beginning of the algorithm's runtime. So I chose to compute it from the mean distance of the 6 nearest neighbors, signifying that there's the average valence of vertices is 6. And then there's my favorite from the year 2022 algorithm called shrink wrapping, which basically computes a distance field and wraps the input geometry with a different mesh. The sort of advantage is that you create a watertight surface without having to close all the holes and having to solve all the topology issues and stuff. So this is the positive thing about it, but obviously the vertices don't match, so there's no guarantee of the surfaces actually being on top of each other, and there's some deviation. And then for future work, we want to solve the issue of self-intersecting shrink wrapping surfaces. So you need to cut out the self-intersections and fix them topologically in order to shrink wrap all the surfaces that are there, even with higher genus. So this is an interesting observation. This basically says how the vertices are ordered in individual files and how they are processed per worker thread. So this is the, I don't know if you can see it, data from 3D scans, standard Stanford Bunny and Nefertiti. This is what artificial / subdivision surface data looks like. There's some kind of regularity there in the different thread coverage, and different miscellaneous processing results such as remeshed or decimated datasets have very irregular worker thread distribution. Now here comes the interesting part. We want to sample or generate some number of unique indices so that we can read the particular spots in memory that we want to process. The trivial way to do this is use a sequential strategy with some stride, if you want. So you could regularly cover the whole memory, but this doesn't actually follow any geometric information. Then there's uniform random sampling. The interesting thing that I also had to solve for this is the generation of unique indices is rather slow if you just want to randomly generate things and then filter them out if they were already covered. So for that I used the Fisher-Yates shuffle, which computes the permutations and leads to 72% speed up. So this is an interesting observation. Here comes the work in progress that isn't done yet because it requires a lot of implementation tasks. So we could as well sample the indices from a different distribution, which is computed from the actual geometry of the already read vertices. And things we want to ensure are feature preservation, uniform tessellation, which is good for the ball pivoting algorithm, for example, for the uniform ball radius, and some kind of adaptive tessellation approaches for different features. The sort of rule of thumb that we use is that for the level of a particular level of detail with some vertices, we estimate probabilities for each vertex in the remaining vertex set, which is obviously still very large. So we need to take a random sample. This is the V tilde, which is slightly larger for the next update, and then we use some statistical methods to extract some sort of reasonable indices from that. Since we're using uniform distributions for this, we use the central limit theorem to estimate how much of the data we want to actually process in the current iteration. So we compute the scores from the previous iteration. We'll show the evaluation of the scores later. And then this value that stems from the confidence level of the normal distribution and the chosen confidence level. Let's say that we want to choose half of the vertices from the probabilities that we compute. Now for this we use an error metric that stems from most of the simplification algorithms, which is just the distance or the deviation from the base mesh, and the vertex distribution metric, which calculates the distances or the edge sizes. And the overall score is evaluated in this gradient form. So how much the current distribution's gradient differs from the target density and the gradient of the error metric. So we don't want to make the gradient, we don't want to deviate too much from the target mesh. This is how it's evaluated. This is the projection to the tangent space. Now, obviously, we don't have any information about how the big mesh, the entire file, looks. So we can't really compute some of these things, especially not the error metric here. So for that, we use an approximation for the gradient, which is computed from the tangential shifts of the vertices. Now, the probability of choosing the index of vertex V from the sampled set is computed using this softmax rule, where we have some sharpness parameter gamma. And here are the descriptions of the parameters in case there's some ambiguity in them. Okay, let's take a look at the actual results for this. Currently only for uniform sampling. We choose a seed, so we have some sort of regularity in the random number generation, and I distributed the process across 14 worker threads. And here are the timings for the preprocessing of 3 test meshes, and this is the Hausdorff distance to the base mesh. You can see that the evaluation the LODs converge. Now for the very large Apollo mesh with 55 million vertices, the total time for the 14 thread LODs is it stretches up to 2 seconds per LOD level. So that's a pretty reasonable thing. And here's also an evaluation for the Lagrangian shrink wrapping of a different scan of the Apollo mesh with almost 1 million vertices, computing the Hausdorff distance to the base mesh. Okay. So the future of this project lies in the following steps. We need a more robust thread sync for all of the operations that we need to do. Then we want to fine-tune the Lagrangian shrink wrapping, not just the self-intersections, but also things like stopping time, which are also important for more generic point clouds. Then we want to implement the stochastic sampling strategy for computing the probabilities. And then we want to try also sampling normals and working with the Poisson distribution and compare the results with the existing methods, for example, for point cloud simplification like the PCSNet. So that will be all for today. Thank you.
So thank you for this presentation with promising results. We can start the discussion. So do you have some questions? There's the first one.
So thanks for the talk. I have a question. It seems to me that what you have presented is actually very much related to rendering point clouds.
Mm-hmm.
And I know that there was a lot of work done in this field by Michael Wimmer and Klaus Scheiblauer, I believe. And they were rendering huge point clouds on the fly, and the key idea they were using was actually to maintain a hierarchy of the points and try to somehow balance it and render it on the fly. So do you think that would be useful also for your approach when you determine the sampling pattern, that you would organize the data in a hierarchy that would be constructed on the fly while you are sampling actually the data?
So behind this, there's a lot of spatial queries that are necessary for this. So obviously, we want to use some sort of spatial hierarchy for organizing the points, as well as updating the mesh. So maybe there will be different clusters or chunks. But I think I know what article you're referring to. Is this the rasterization of 2 billion points?
It's one of them. I think they had like 5 or 6 papers on the topic.
Yeah, I think I've seen it. So yeah, it's a good insight. Thank you.
Hello. I guess the question has been partially asked by Yuri now. So the hierarchy is one thing. Can you go back to the results slide? It seems to me that the coarser levels of detail shrink the object, right? This is
this is due to shrink wrapping. This is a particular symptom of not having a proper stopping criterion for shrink wrapping. If you have let me take a look at I don't have it here, but if you have the whole point cloud tessellated by the ball pivoting, you don't shrink anything.
I understand, and it's common to LOD, to simplification schemes. If you do something like edge collapse, you would observe similar problems, that the object only ever gets smaller. But did it occur to you that you could use some sort of stratified sampling where you make sure that if there is some vertex inside a volume of space, at least one representative is selected from that volume of space?
And would that be, for example, a bounding box, or what kind of volume are you referring to?
Well, I mean, that's open to debate. Hierarchy would be one answer, but a regular grid might actually suffice. if a cell in a regular grid is occupied, then at least one vertex would have to survive, and then the shrink wrap cannot, sort of cut that away, that portion of space which is actually occupied.
Yeah, I think this is a good insight, but the problem with shrink wrapping is that it's a numerical method for evolving the entire surface. So you basically have a starting mesh and you end up somewhere after some amount of time steps. And I initially had the idea of doing some sort of statistics within the distance field, like if the surface isn't moving too much, then you just terminate the evolution. But then you also have the challenge of having some sort of hole within the mesh or within the point cloud and the surface protruding through it. So you essentially have no way of stopping it. And for this, I think it needs a lot more research. Thank you.
Thank you.
My first question is that, like, your goal is to skip the preprocessing step, and you're using some kind of generation of indices instead. And what is the comparison of time needed for the computation of the indices in comparison with the preprocessing techniques of the state-of-the-art methods? Is it like really faster, or?
This is the whole thing. This is just the time from a particular sampling, the start of the sampling, until it's done, until you can actually see it. Or
okay.
So this is the whole the whole time, and comparison. Well, I guess you would need to run it on this large data set, but the sort of benefit in here is that you choose a vertex cap, and you don't need to process all the vertices from the original file. This is the sort of marketable trait of this algorithm, and sort of obviously it requires some sort of pre-processing. That's what I wanted to say. But the pre-processing is fast enough because you're only looking at a certain amount of data.
Okay. There's.
So do you work with the idea that actually the data would be shown on the fly while it is being loading? It is progressively being shown in more and more detail. Is it?
Yes.
Because
Yes. This is happening in a background process of some kind, and then you can just rotate the mesh in a certain LOD until the next LOD step is available.
I see. So for the times there, I mean, you would basically go along this curve. But you would see also intermediate results.
Yes.
So you wouldn't have to wait for like 2 seconds, but you would see something at least before, right?
Yes.
That's good. Yeah.
And I also played with the sampling frequency. I actually made it exponential because first you need only a small amount of vertices to show something, but the next iteration, the next LOD will be comparably fast. You just reach the nearest bottleneck in the LOD steps. Let's call it that.
Okay, thank you.
We do have time for one last question. So I can ask the last question. It might be just an idea when I'm thinking about that during the meshing step, the Lagrangian wrapping of the point clouds, isn't it possible to somehow reuse the information from the big old input model, like the edges in the file, to optimize somehow the iterative process of the mesh?
Well, I can imagine that you can sample a certain amount of triangles to compute normals, but for that you can also use the gradient of the distance field. So there's the computation of the orientation of the surface is actually the pivotal part in this reconstruction step, because you need the oriented point cloud, for example, to produce watertight Poisson surface. So you could use that information to compute normals. This is from what I imagine.
Okay, that might be one way. Okay. Maybe one last question, and we don't have other questions, so we can thank the speaker again.
Swing to the beat where the pixels play, from rendering to VR. It's a pixel away.